So next up, we're going to be in section 2.6, talking about numerical approximations. We're skipping a couple sections real quick because I like to have this material closer to the start of the class, but we're going to go back and fill in those sections after this. So this is the overview of everything that you should get out of this set of videos. If you don't feel like you learned these objectives, that would be a place to start asking questions. First thing we're going to talk about is an intuition for the idea that derivatives tell us how a function is going to behave next. That's how we build approximations, and it's going to be really familiar to you from other classes. Then we're going to talk about the algorithm for Euler's method, the particular approximation that we use, and then we're going to implement it by hand once and then using a spreadsheet. But if you know any programming language, you could implement it there too. And then sort of what I want you to get out of this entire set of videos is really the idea behind the numerical approximation. So we're going to learn a whole bunch of different ways to solve differential equations in this class, but there are many more differential equations out there that you can't solve using the methods that we'll learn. So chances are, if you encounter a differential equation like in the wild, this is a method that's going to be useful to you to understand the process behind, if not necessarily to use the method yourself. So that's why we're going to spend so much time up here, building an intuition for why this works so that you can kind of understand how the way that we solve differential equations in a lot of applications works. So the first thing that's going to help us understand what a numerical approximation is to go back to direction fields. And that's why I like to have this early on, because direction fields are still fresh. We just covered them last week. But, just because they are new at least, we're going to kind of be careful and actually show what we're talking about here. So here's a direction field. We worked with them last week. Just ignore that my arrows are lopsided and whatnot. That's the general idea. So we talked about the idea that direction fields would be for a differential equation dy dx equal to f of xy, and having initial condition like y of x0 equals y0. And so our general approach to direction fields was that we plotted f of x0, y0. Well, we didn't really plot f of x0, y0. We plotted arrows with slope f of x0, y0. For a bunch of potential points. And then we just started from our current or intended initial condition, x0, y0, and then we followed the arrows to sketch the curve for y of x. So if that's our x0, y0 that we care about in our initial value problem, then we would just follow these arrows. We would say, that's what y of x looks like. And when we were sketching those curves, what we were doing is we were building an approximation. It is what the curve y of x looks like, but sort of when you sit down and do it on paper, you're making your best guess with the arrows that are available to you. And this whole process that we use is related to linear approximations as you learn them in your calculus classes. And when I say calculus classes, I mean like calculus 1 when you first learn about derivatives, and then calculus 3 when you learn about like multivariate derivatives. We're going to flesh that out a little bit more here. So we're just going to think about connecting this to calculus. And I'm not doing this because we're going to spend a lot of time thinking about calculus in this class. It's mostly just going to be a tool for us, but that is sort of the understanding that you have. And so I'd like to take this new tool that we're going to learn and try to connect it as much as possible to something that's already familiar to you and you've kind of already struggled through the details of. So in any calculus class, you would have learned that you can take derivatives. So you should be able to start from y equal to x squared plus 1 and find the derivative. Y prime of x equal to 2x plus 0. And using the notation that's more common for us, that would be dy dx equal to 2x. So you're very comfortable with this forward direction. Given y, find y prime. And our new way of thinking is always going to be to assume that you're given y prime, or the derivative, and then find y again. And then after you first learned how to just compute derivatives, probably you would have learned about the idea of what a derivative is. So you would have learned that derivatives, actually, let's put that on the next line, are the slope of a tangent line. So if you had x and y, and here's your cx squared plus 1 would look kind of like that. Then at any point on your curve, you would have said, oh, the slope of this line is your derivative. And so then you would have used that fact to build linear approximations. So that would be something like y is about f evaluated at a point plus the derivative times the distance between some x you want to get to in a, or in multivariate calculus, like z is equal to z0 plus fx times x minus x0 plus fy times y minus y0 for the tangent plane, which is just a linear approximation in more than one dimension. And if you kind of like look at this picture right here, hopefully it looks like what we did with direction fields. So you can kind of see that when you went in the kind of forwards direction of given y, compute its derivative, and then that happens to be the slope of the tangent line. That is related to when we have the direction field, we're given a bunch of slopes of tangent lines, and then we can follow those things to recreate y, which we didn't know before. And so kind of what's important to note here is that that same next step that you learned in your calculus classes, building linear approximations, is the exact same next step we're going to have when we're building our approximations to differential equations. So Euler's method is just the idea of using derivatives for linear approximations applied to ODEs. And I don't want to take you over that 10-minute limit, so I'm going to stop here. We're going to go ahead and get the algorithm and run our first practice problem in the next video.